Hello, in this video I'm gonna be talking about the fiber product of schemes. So let X and Y be a pair of S schemes. We define the fiber product as a scheme together with a pair of morphisms called projection morphisms such that the diagram commutes. It would also satisfy the following universal property. If Z is any other scheme with morphisms to X and Y making the diagram commute, then there exists a unique morphism from Z to the fiber product making the obvious diagram commute. Similar to tensor products, we must also verify that they actually exist. The proof of the existence of fiber products is somewhat tedious, so I'm not going to include it here, but it can be found in its entirety in Hartshorne or Mumford's second red book or Quinn-Lew's arithmetic curves. One of the proofs of this theorem uses the following proposition. If A and B are C algebras, then the fiber product of spec A and spec B over spec C is the spectrum of the tensor product of A and B over C. The morphisms of schemes are the ones induced by the respective morphisms of C algebras. Next, recall that n-dimensional affine space over R is defined as the spectrum of the polynomial ring in n variables over R. So we have the following proposition. N-dimensional affine space over R is isomorphic to the fiber product over spec Z of the spectrum of R and n-dimensional affine space over the integers. The proof of this proposition boils down to checking that the tensor product over the integers of R and the polynomial ring in n variables over the integers is isomorphic to the polynomial in n variables over R. This in turn follows from a more general fact that can be checked with a universal property of tensor products. Let B be an A algebra, then the tensor product over A of B and the polynomial ring in n variables over A is isomorphic to the polynomial in n variables over B. We get an interesting corollary by setting B to be a polynomial in n variables over A. The next propositions come from Quinn-Lew's arithmetic curves, and one can see the similarity between the corresponding properties for tensor products. As for the proof, for the first one, it is immediately verified that X satisfies the universal property of fiber products with projection maps, the identity, and phi. For the second and third, it can be checked that they satisfy the corresponding universal properties. We also have the following proposition. Let F and G be morphisms of S schemes. Then there exists a unique morphism of S schemes between the corresponding fiber products which makes the diagram commute. So this follows immediately from the universal property by taking the composition of the projection maps and F and G. Fiber products allows us to define several important concepts like separatedness, properness, base change, among other things, but I'm only gonna do base change in this video. If we have an S scheme X, base change is more or less, like its name implies, changing the base to another scheme. This process of base change is transitive in the sense of the following proposition. Finally, I might make use of the following propositions and definitions found in Hartshorne in a follow-up video, so I'm including them here. Let's start by recalling the definition of residue field. Let X be a scheme. The residue field of X in X is defined as the quotient field of the stock of the sheaf at X by its maximal ideal. Recall that the stock is a local ring, so there is a unique maximal ideal. We have the following proposition that is exercise 2.7 in Hartshorne. If K is a field, to give a morphism from the spectrum of K to X, it is equivalent to give a point X in X and an inclusion from the residue field to K. The proof more or less follows by following around the unique prime ideal in the field K. A slightly different approach can be found in Quinn-Lew in page 46. Next, let F be a morphism from X to Y, and let Y be an element of Y. Let spec from the residue field to Y be the morphism obtained above. Then the fiber of F over Y is defined as the fiber product over Y of the spectrum of K, Y, and X. So now we can define the formations. Let X0 be a K scheme, so a spec K scheme. A family of the formations of X0 is a morphism from X to Y with Y connected together with a point y0 in Y such that the residue field ky0 is isomorphic to K, and ky0 is isomorphic to x0. The other fibers xy of f are called deformations of x0.